Nashan, speaking about every data structure deserves lock-free memory reclamation. Actually, before you begin, one thing I want to note, just like the keynote this morning, we'll be taking questions online as well. So we're in studio too, and I'll sort of interleave live questions and online questions. Take it away.
Okay, thank you. So after we solved one parallelization problem, let me talk about another parallelization problem of a lock-free data structure and how to do memory reclamation. In fact, in this talk, I want to talk about Alice. So Alice is a designer of lock-free data structure. Now you might wonder what is lock-free data structure. So lock freedom is progress guarantee, and guarantee system-wide progress even under a bad scheduling. So this guarantees that the system progress even if we have a thread that is delayed or printed out of CPU or even crashed. And such data structure cannot participate in deadlocks or live locks. And also they perform quite well in practice because threads tend to do real work instead of just waiting for each other. And Alice, being a capable researcher, has some very nice idea or some data structure, and she sits down, write a lot of code, then write a nice paper, which she intends to submit, well, probably to Uppsala 2019, as you should all do. Which is exactly where a problem started to happen, because Bob is a designer of lock-free memory reclamation scheme. And then he gets Alice's data structure, and he's saying, like, your data structure works perfectly well. I run it, and it provides perfect performance for 10 seconds. But afterward, my system ran out of memory because we never reclaimed anything. And this is a problem, but Bob, being a capable researcher by himself and designer of lock-free data structure, has some suggestion to Alice. So first, he suggests to use epoch-based reclamation, but Alice don't want to do this because it's not lock-free. And then Bob suggests to use a hazard pointer or optimistic access or Zebra Plus or automatic optimistic access or stack trace or a bunch of other schemes present in the literature in the last years. But Alice don't want them because all these schemes do not fit into her data structure. And now you might wonder, so why it's so hard to fit this reclamation to the data structure, and also how the hazard pointer scheme works, which forms the basis of all these existing data structure and also for the new one I'm going to present. So suppose we have a lock-free linked list. And now we have a thread 1 that now navigates the list and look for node 4. But right now, it's actually in the middle of navigating the list. And right now, it looks at node 2. And because we're talking about concurrent algorithm, we might have another node, node T2, that right now want to remove node 2. And clearly, if node 2 would just free this node, then thread 1 continue navigation, access this node, and crash. So clearly, this is really bad. But then, how to solve this problem? How to reclaim memory? So there has a pointer scheme and many other conceptually similar schemes. So this problem introduces something that has a pointer, which is a public pointer saying to all threads in the system, look, I am now accessing node 2. Please do not reclaim it concurrently. And now when thread 2 remove this node, instead of reclaiming it, it just retire it. And then the reclamation scheme will just wait a little until thread 1 finish accessing this node and then reclaim node 2. So this is a very nice scheme. It actually works. But not anything is solved yet. And in fact, the hardest part is still ahead. And things work more or less fine when there is only one concurrent node removed. But what happens when there are two nodes concurrently removed from the list, both 2 and 3? And now, in fact, there is no hazard pointer pointing to node 3. There is no other thread in the system that actively right now accesses node 3. And so node 3 is not protected, which means that it's going to be freed. And now, if thread 1 continued navigating the list, it would access node 2, then access node 3, and then crash. And here, what Bob tells Alice, well, look, this is your problem because you write the data structure in such a way that it accesses a node that was removed. So go on and fix your data structure. But Alice don't want to do this because she designed a very good data structure and she wants a reclamation scheme that fit into her data structure. So how can we build a reclamation scheme that fit into Alice's data structure and not fit into how Bob thinks Alice's data structure should look like? And this is exactly the three-axis scheme means to solve. So the three-axis scheme is a reclamation scheme. It provides a full lock-free guarantee. So it guarantees that no matter how thread delayed, wait, crash, it's still able to reclaim memory. It is applicable to almost any data structure, in fact, to any data structure I'm aware of. And in addition, it can be applied automatically just by running a Clang plugin. So all Alice needs to do is just put this weird text near her a function, and then run the Clang plugin, which will take care basically for anything, all the memory reclamation part. So how does this free-access scheme work? So the free-access scheme depends on two parts. One part is a lock-free mark and sweep algorithm, which I presented here 3 years ago at UFSLA 15. And the lock-free mark and sweep algorithm was shown to be able to reclaim only unreachable object. It does not wait for thread, does not require handshake, able to function well. However, it requires the algorithm to be presented in some normalized format. And again, Alice don't want this normalized format, don't want someone to tell her how her data structure should look like. And to complement this, we generate a lock-free root gathering mechanism that is lightweight, generic, does not assume anything on the data structure, which is the main contribution of this work. So let me start by a quick reminder of how mark and sweep garbage collection work. So mark and sweep garbage collection start by collecting roots. So in this case, it's something like the head pointer and also pointers held by the threads. So in this case, it's node 1 and 2. Then it performs marking. So node 4 is reachable from 1, and node 3 is reachable from node 2. And then these two nodes here, marked by F, are not reachable by anyone, and so they can be reclaimed. And the main challenge to do this in a lock-free setting is that we do not know anything whether thread, what is the status of this thread. So we need in some mechanism to gather the roots of the thread without knowing anything, whether it's stuck, is printed out of CPU, is waiting. The way the free access scheme work, which is the main idea behind this work, is the idea to partition every operation, the execution of every operation, to an alternating periods, and between periods that only read from the memory and periods that only write to the memory. So if we put a timeline of the operation, it starts by reading something from the shared memory, then write something to the shared memory, then read some more, then write some more. And the idea is that almost any operation can be decomposed in this way. So how does this partitioning help us? So let me start with a read-only period. So what is a read-only period? So basically, we're talking about a thread that navigates a linked list. So for example, looking for a node 4. And the characteristic of read-only access is that roots change very frequently, right? Every time thread visits a new node, the set of roots actually change. But on the other hand, a read-only period is restartable. Because it never modifies the shared memory, So it's never a problem just to tell the thread, okay, what you did, there's some garbage collection going on, just restart the operation locally. And so for read-only periods, the algorithm publish the set of roots at the beginning of the period, and then if some reclamation is going on, the thread just restart to the beginning of the read-only period. But we also have write-only period. And clearly write-only period cannot be restarted, right? Because if we restart a write, then we might apply same modification twice. But on the other hand, when the thread modifies the shared memory, the main observation is that it doesn't load new pointer to the set of roots. So the set of roots actually remains static. And so for write-only period, all we need to do is to publish a set of roots at the beginning, and then it just remain constant throughout modification to the shared memory. And so the overall algorithm with free access the operations start by some read-only period, and if some reclamation is going on, the thread will just restart to the beginning of the operation. Then the thread move on to writing. So before starting to write, thread just publish the current set of roots, and then do its modification. And if there is some garbage collection going on, nothing changed. After finishing writing, thread again start reading. So we have already actually have the hazard pointer, the set of roots published, and then there is some garbage collection going on, the thread just restart to the beginning of the read-only period, and so on and so forth. On top of this, we wrote a Clang plugin. The Clang plugin mainly categorize or classify the instruction as read-only, write-only, basically load instruction or store instruction in atomics. Then it identifies the boundaries when the operations switch between read-only and write-only period. When the threads start writing, the Clang plugin insert an instruction to publish the set of roots here has a pointer. When the threads start reading, it basically stores a set of local information. And then during read periods, if there is some garbage collection going on, the Clang plugin automatically insert go-to statement to the beginning of the read-only period. So this is the main idea of the algorithm, and it actually works very nicely and very simple to use. But now we still have one very important question to ask, and this is like, how much does it cost us? Like, how much does it cost to have all this saving data and publishing information in runtime? And so to answer this question, we evaluate the system, the memory reclamation scheme. We evaluate it compared to various other reclamation schemes. So the first one is just no reclamation, which is what Alice started with, just run the operation. Again, it worked perfectly well for 10 seconds, but then it doesn't. The automatic optimistic access scheme, again presented here 3 years ago. Free access scheme, this work, reference counting, has a pointer, and in addition, also has a pointer with fence elision, which is actually not strictly lock-free because it makes some assumption of how the operating system know about the threads, but in practice, it's some reasonable compromise. To evaluate this, we used a long linked list, a short linked list, and a hash map, and we use a machine with 64 cores, and the workload is write heavy to really exercise memory reclamation scheme hard. So here are the results for the long linked list. So here on the x-axis, you see the number of threads between 1 and 64. And on the y-axis, you see the relative throughput compared to no reclamation. Recall that no reclamation is no overhead. So this is sort of the unachievable baseline. And here you see that the free access, the black bar, actually is able to deliver better performance than all other reclamation scheme, and very, very close, within less than 1.5% compared to no reclamation. So not only this is very simple to use, it also delivers great performance in this case. When we move to a short linked list, so here operations are shorter, there are much more contention on the list, so those are slightly different. So here the overhead of the free access is slightly higher, but still in most cases it's much faster than other reclamation scheme. One interesting exception here is a hazard pointer memory barrier here. And this scheme, because it's able to reclaim memory really fast, so it's able to deliver deliver better cache locality, so reuse memory fast. So you see that actually better than no reclamation, but this is again not strictly lock-free. And again, free access scheme is able to deliver better performance at all other reclamation scheme and quite close to just not reclaim anything in the first 10 seconds. And finally, moving to a hash map. So hash map operations are extremely short in the average case. We visit just a single node. And this is write heavy, so overhead of memory reclamation here is much higher. And again, for most of the cases, free access scheme just deliver great performance. Again, the exception here is a 64 threads case, where here also the hazard pointer reclamation scheme is able to deliver a slightly better performance than the free access scheme. And practically, only for this case, I should be able to say that at least now there is some cost of being much simpler to use and much more general than the hazard pointer scheme. So just to conclude, so existing lock-free reclamation scheme are very hard to apply. The free access scheme is a lock-free reclamation scheme. It depends on two components: lock-free mark and sweep algorithm presented 3 years ago, and the generic root gathering mechanism which partition the execution into read-only and write-only periods. And the benefit is that this scheme is able to deliver fully lock freedom guarantee, no matter how threads are delayed, crash, or whatever. It's very easy to apply. There is no need to modify the data structure. There is no need actually even to modify the code a lot. Just use the compiler plugin and also deliver quite great performance. So on behalf of Alice, I want to thank you very much, and I'll be happy to take questions.
Thank you. We have now a couple of minutes for some questions.
Hello, this looks quite great. I'm Matthew from Cornell. I was wondering, when I frequently write lock-free data structures, which of course we all do, I have a tendency to use slightly weaker memory models than sequential consistency. How does that play in with your strategy? Am I stuck at sequential consistency, or does it all work out?
We certainly need, the weak memory ordering is certainly a big issue here, and we have to carefully place fences accordingly. This is a little more related to the component that was already done 3 years ago, so I didn't get into these details, but there's certainly a lot of effort to do this correctly, and there's certainly a lot of subtleties here, how to place the fences correctly.
But I'm good. I can use weak memory. But I can use weak memory.
I mean, surely yes. Basically, only thing that here I require is that the boundaries between write and read are well defined. And yes, between write and reads, I do need a strong fence, which in most cases, you anyway have. But this is a requirement, and yeah, we do this. And yeah, you can use weak memory.
Anybody else?
Hi, Emery Berger, UMass Amherst / Microsoft Research this year. So question for you. So you mentioned that no reclamation, you said, is the unachievable baseline. I mean, I wonder if that's an appropriate baseline because in my experience, when you actually are doing some reclamation, you get the benefits of locality, right? So you have recycling in the cache. And I've done some experiments where I just had something do bump pointer and compared it to using almost any reclamation scheme, and bump pointer is invariably much worse because it sort of spreads everything out all over memory. So I just wondered if you'd considered looking at another baseline, if you thought of maybe putting in, running this thing with malloc free instead of relying on GC, or what your thoughts would be.
Yeah, I mean, in my so first, I should notice that because it's more like a garbage collection scheme, I also don't reclaim memory very fast. So compare, for example, to hazard pointer, I don't get like the benefit of reclaiming memory very fast, which as you saw in the short linked list, has some overhead. I didn't saw like significant, but I mean, it might be something interesting to check.